This video is an introduction to the physics concept of friction, and we will take a little bit closer look at one type of friction known as air resistance. Now, friction is actually a variety of forces. It's any force that opposes and affects the motion of objects. So friction always acts in a direction opposite to the motion relative to a frame of reference. It arises from interactions between surfaces. So if two things are touching each other, then friction can come about. When solid objects come into contact, the friction is mainly due to irregularities in the two surfaces. So for example, here are two boards, and if we rub them together, they'll generate friction. Now, if this were a pair of hands, we might feel some heat, and people say the heat is caused by friction. That's not exactly the straightforward explanation, but it's close enough. Friction is a set of forces, and it can cause energy to be released when these two things move. Now, in this particular case, what's happening on the very microscopic level is that there are a lot of irregularities on the surface, and they catch on each other, you might say. But on an even finer scale, they can be as smooth as you want them to be, and they'll still interact because of electrons moving close to each other and nuclei moving past each other. So there'll be all sorts of interactions that cause frictional forces. Now, friction isn't always a bad thing. In fact, without friction, you wouldn't be able to walk. When you put your foot on the floor, you push backwards. There's some friction there, and that's what helps propel you along the floor. If you didn't have that friction, like if you're walking on ice, you don't get very far. Friction is what holds you on the road. It keeps you between the ditches whenever you're in your car, because there has to be friction between the tire and the road in order for the car to be able to go around a curve. So friction is a force, or really it's a set of forces, and because it's a force, if we consider all the forces acting on something, we have to consider friction. If we were drawing a vector diagram, we would have to draw an arrow representing friction, such as this diagram. Now, we call this a free body diagram. What that means is that it's just a representation, and it has vectors for all the forces at work. The forces in this particular diagram show a 10 kilogram block, but you don't have to actually have that block there. But what a free body diagram usually does is it does put the origin in the center of the mass. So we see all the tails of the vector arrows touching in the center of the 10 kilogram block. There is a force that's pulling on the block. We call that the applied force. Then there is friction that resists that motion, and friction is in the opposite direction. There are two other forces shown here, gravity and the normal force. The normal force and gravity also oppose each other, but there's no motion in that direction because those two forces are balanced in this particular diagram. When friction is present, an object may still move with a constant velocity. It's just that the applied force and the frictional forces would have to be equal, so the arrows would have to be drawn to the same size. This particular diagram, it looks to me like the applied force is a little bit greater, and so this object will be accelerating toward the right side of the screen. If friction balances the applied force, then the object can still move, it just will not accelerate. So it'll move at a constant speed in a straight line. If friction and the applied forces cancel each other out because they're equal but in opposite direction, and the normal and gravitational forces cancel each other out, then this object is at equilibrium. It can still move, it just will not accelerate. It won't change its motion. I've mentioned that normal force several times. We haven't talked about that yet, but a normal force is a force being applied by a surface on an object, and it's always perpendicular to the surface. So if this object is sitting on the table is pushing on it. I know that's hard to imagine that an inanimate object can exert a force, but if you push down on the table pushes back. If that were not the case, then the object would be accelerating in a downward direction. Since it's not accelerating, there must be an equal opposite force going up to counter the weight. That opposite force that goes perpendicular to the surface is called the normal force. Now, if that book or object is at rest on the table, does it have friction? Well, not really. We say that friction opposes motion. So unless the book is sliding or moving somehow, then there is no friction, technically speaking. In some books, you might read that there's something called static friction that exists whenever an object is at rest, but you only really think about static friction when you are trying to move the book. So if the book is sitting still, it doesn't really have friction. We tend to think of solid objects a lot when we talk about moving things like books or cars or people, but gases and liquids can also move. In fact, their name, fluid, comes from a Latin word which means to flow. So fluids are anything that can flow, and fluids can also experience friction. Fluid friction occurs as an object tries to push the fluid aside and out of the way. It can occur when a solid object moves through a fluid, such as a car going through air. In this particular case, we call the fluid friction air resistance. Air resistance is just a name for a type of friction. So here we have some sort of box that's being pushed. There's a force being applied to the right. Well, there are frictional forces that are opposing that motion. If the friction and the push are equal but opposite in direction, the box will move, but it will move at a constant speed in a straight line. It won't change its motion unless there is a net force, only if one of these forces is larger. Well, if something's moving through the air, it can also have a frictional force. We just usually label it air resistance. If it's falling, then the force that's pulling it down is its weight, it's the gravitational force. But that object, as it falls, will encounter air. Air molecules will resist its motion. And so air resistance is a form of friction. Air resistance is friction, and so we do draw it in the opposite direction of motion. If something's falling, then air resistance would point up if you drew a vector arrow. If it's an airplane, as modeled here, then if the airplane moves to the right, friction is drawn to the left. It points toward the opposite direction of the forward motion. If it's going in a diagonal, then the air resistance will be drawn diagonally as well in the opposite direction, 180 degrees. Now, friction is really a complex topic, and I don't want to go into very much detail at this time. There's lots of different kinds of friction. I mentioned earlier static friction. When you push things along a surface, we call that sliding friction. We have all sorts of different fluid frictions. For our purposes, we only need to know that friction is our category for forces that spontaneously oppose motion. So they arise when something moves, and they always oppose that motion. I do want to talk just a little bit more about the special case of air resistance, since that will come up several times in examples in the next few weeks. You experience a force due to air resistance anytime you move through the air. But maybe you've done this before. Maybe if you roll your window down in a moving car and stick your hand out, you can feel the air pushing on your hand. That's air resistance. If the car goes faster, you feel more air hitting your hand and you feel a greater force. You feel more air resistance. If you stuck your physics book out the window instead of your hand, you would feel even more air resistance. This shows that air resistance depends on the amount of air you encounter. So it depends on what we call the frontal area or exposed area to the air. So air resistance is proportional both to the speed that you're moving through the air and to the amount of area exposed to the air, so the frontal area. Let me show you a little demonstration that shows the importance of this frontal area or amount of surface exposed to the air. In this demonstration, I'm going to take two pieces of paper. Now they have equal mass, but I'm going to ball one of them up. So now it has much less exposed area or frontal area when it falls. So I'm going to drop both pieces of paper at the same time. Watch what happens. The balled mass hits the ground much sooner than the other paper, which has a lot more frontal area. It's encountering a lot more air and therefore a lot more air resistance. So air resistance depends more on the frontal area than it does on mass. This time I'll drop them side by side. I'll try to start out with small frontal area, but because of the random nature of air, it'll knock the paper sideways, and again, the mass hits first. I did this lots of times, and it always worked out the same. The ball hits long before the other piece of paper, even though they have the same mass, because the paper has more air resistance. Now, is there a way to make both of them hit at the same time? Watch this demonstration. I set the ball on top of the other sheet of paper, and now I drop them, and they fall at the same rate. Little trick there. That is the effect of air resistance. Depends mainly on frontal area and the speed of the object. In this demonstration, So, what would happen if there were no air? Now how would two objects fall? If I dropped the two sheets of paper, would there be a difference? Let's watch this very famous demonstration. It's a little bit hard to see because it's really old video, but watch this.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? How about that? Proves that Mr. Galileo was correct in his findings.
Now, that's a very famous demonstration done on the moon 50 years ago. And if you could see it, what you see is the hammer and the feather both fall at the same rate because there is no air on the moon. You can look that video up online in case you couldn't see it so well here on my video. So the feather and the hammer fall with equal accelerations because they're both being pulled toward the surface of the earth by gravity, but they're resisting that pull because of their mass, and there is no additional air resistance to slow either of the objects down. The hammer does in fact experience some air resistance, It's just that the air resistance is very small compared to the force being pulled downward. So the net force is very high for the hammer. Whereas for the feather, the air resistance is a significant part. It's not quite equal to, but it is a significant, it's very close to the force of gravity pulling it down. Now, if you've ever dropped a real feather, or if you watched that piece of paper as it was falling in the slow motion videos earlier, you saw that it often kind of hits a speed and then goes at that speed, especially like that last demonstration with the paper when I put one piece on top of the other. It falls really fast at first, and then it still goes down, but it doesn't speed up as much. And in fact, what it can do is hit something called the terminal speed. The terminal speed, or end speed, is a speed at which acceleration of a falling object is 0. And what's happening there is the net forces are balancing. They're causing an equilibrium. The object still falls, it just doesn't speed up. So as an object falls, air resistance gets greater and greater because of the speed. When you go faster, you hit more air molecules, and every air molecule you hit slows you down a little bit, or slows down your acceleration. So if you hit enough air molecules, it actually causes an equilibrium. If we include the direction, sometimes this is called the terminal velocity, but typically terminal speed is used because we're usually talking about the downward direction. Point is that friction is a force, and because it's a real force, it can contribute to the net force that's acting on an object. And if the net force is 0, then the object can move, but it does not accelerate. It doesn't change its speed anymore. So that's what I'm saying in this little clip. 0 acceleration means an object will maintain its velocity. It doesn't speed up, it doesn't slow down, it doesn't change direction. Here on the Earth, a falling feather encounters air. And the air resistance is quite significant because of the great amount of frontal area compared to its small mass. It encounters a lot of air, and that air force, that air resistance, can balance its weight very early on during its fall. A hammer does encounter air resistance, but in order to build up so that it could actually balance its weight, so that the air resistance could equal its weight in the opposite direction, that hammer would have to go very, very fast. And so it would have to fall from a great height, thousands of feet high. A hammer will reach a terminal speed. It will hit a speed at which it no longer accelerates, but it would have to be very, very high. Lots of animals and plants take advantage of this air resistance due to frontal area dependency. Here's a flying squirrel. They don't really fly. They just sort of parachute or glide. It opens up a large air skin flap on either armpit, and as a result of this large frontal area, it can have a large air resistance. Very small weight, and so it can hit a terminal speed, and by changing just slightly which direction those air flaps are pointing, it can maneuver a little bit. A person, a human, also has a terminal speed. If you jump out of a very high airplane or helicopter, you fall faster and faster, but the amount you accelerate gets a little bit smaller each second. In other words, you are going faster, but you are not going, you're not changing your speed as fast, up to a certain point. And that certain point is around 120 miles an hour, about 53 meters per second. Once you're going that fast, you're hitting so many air molecules that the air resistance has built up to equal your weight. Now, if you weigh more, you might have to go a little faster. So a heavier person could attain just a little bit greater terminal speed than a lighter person. It might not be much of a difference, but it would be significant enough that after falling hundreds or maybe thousands of feet, the heavier person would probably get to the ground first. Body orientation, how much frontal area you expose to the air, definitely has something to do with it. If you spread your arms out like the flying squirrel we just saw, then you're going to encounter a lot more air than if you just sort of tuck your arms to your side and point your head straight down. So the way you orient your body will change your frontal area, or the amount of area exposed to the air molecules. So again, a heavy skydiver and a light skydiver can jump out of an airplane at the same time. And if the heavy person spreads out like a flying squirrel and the light person instead falls head first, the light person could in fact go faster toward the ground than the heavier person. A parachute is just an extreme example of air resistance. Now you have a great frontal area, you encounter a lot of air, and so you get a lot of air resistance. And it can actually slow your terminal speed down so that now you're only going about 10 to 20 miles an hour instead of 120 miles an hour. Here are some parachutists in formation. And you notice they're trying to go as slow as possible. They're still falling, and they're falling very fast, probably 120 miles an hour, but at least they can stay up, if they're high enough, they can stay up there for a few seconds. At low speeds, air resistance is not very significant, and so we can ignore it for most part. But if you're going very fast and you're here on the Earth, then you have to take air resistance into account. If you hold two objects that have roughly the same size and shape and release them at the same time, then you'll see them strike the floor at about the same time. But if you drop them from a very tall building or out of a helicopter, then you would notice the heavier object would definitely hit first because it would have a slightly greater terminal speed. It will be going faster, even though it's not accelerating anymore. Once it hits its terminal speed would be greater. Here's actually a picture of that in action. This is a golf ball and a foam ball of about the same size. And so they have about the same size, about the same frontal area, but the golf ball has a greater mass. And so what you're seeing are each of these pictures, there's 5 different pictures here that are pasted together basically, are at the same time, and you see that the golf ball is definitely picking up a little bit more speed than the foam ball. So here's a question for you to think about. Which you think would experience a greater air resistance force? A falling piece of paper or a falling elephant? You might have been fooled by the question. It's not which one is affected by air resistance the most. It's which one would you have to draw a bigger vector arrow for. The elephant has a larger frontal area, and so it would encounter more air and therefore would have a greater air resistance force acting on it. It might not slow the elephant down very much, but that would be a much larger force than acting on the paper. In fact, the air resistance on the paper, if the air were not moving, if there were no wind, the air resistance can never be more than the weight of the object. It can equal it, but it can't be greater than it. Let's think about another question here. If a heavy person and a light person open their parachutes together at the same altitude and each wears the same size parachute, who's going to reach the ground first? Well, even though they have the same frontal area, the same parachute size, the heavy person does have a greater mass and therefore does experience a greater pull of gravity, and so they will hit a slightly higher terminal speed than the light person, and so the heavier person should hit the ground first. Now, those are just some thought questions. We're not going to go into too much detail really about all this air resistance stuff, but I just thought this was some interesting effects of friction. Friction is something that sometimes we will ignore, and sometimes we have to take it into account. And so you have to listen very, very carefully whenever we're talking about force problems, whether or not friction is a factor or not.